Let's do it. All right, this is a fun one. All right, it's been a while. Just think of I missed you guys. Hope you've not missed me. All right,
a long 2 weeks.
well, it was a long 2 weeks.
Yeah.
Yeah. Okay. Um, so last time we talked about beet trees and heaps. If you didn't see that, you should catch that up because the homework is on that. This time we are doing recurrence formulas. You saw in the lecture, divide and conquer, right? Yeah, you guys saw divide and conquer.
Yeah.
Now we're gonna talk a little bit about analyzing algorithms. You kind of saw this in Mavo a little bit. You saw this in Intro to Computer Science. We're going to go a little bit more in depth and go through really all of the ways, the methods of solving recurrence formulas, so that you guys can do it yourself. Okay. For example, this is pseudocode, right? Given this pseudocode, first of all, in parentheses, what is the algorithm? What does it do?
It's sort of like halves.
It sorts, is said in the name of the function, it sorts it, but it's called merge sort. Basically, each time it divides the whole array into two and calls itself on each half. And calls itself and calls itself until we get to only one element. It doesn't have to organize it, and then it puts them back, it merges them back. Okay, so that we're gonna talk about. Did you talk about it in the lecture? How merge sort works?
Not the last.
Not the last one. Okay. What's more important than the algorithm itself is what is the time complexity of an algorithm. We'll talk about this one, the algorithm when we talk about sort. But what is the time complexity? How do you? Is it O of n? Is it O of n squared? What is it?
So again.
Why?
It's we draw a tree, we have log n letters.
A recursion tree?
No, the
Recursion tree.
So
The recursion tree.
yeah, and every node, like the sum of the times for the nodes for every layer is n.
Okay.
We have n layers, then log n layers.
All right. So we're gonna do that formally. We're gonna talk about how to solve these recurrence formulas formally. This is first before we even go to the recursion tree. T of n is our function, right? It gets an n and it does something, right? It splits it into two, and then it puts them back together at the end. So here you get this line of code is doing the same the same algorithm on n divided by 2. And then this one is line 3, where we also split it into half. One of the times it's rounded up, one of the times it's rounded down. And at each level, at the end, we have to merge it, right? And that takes theta of n. All right, so this is our formula. And this is our stopping. When we get to the end, we only have one element, that's where we stop, and it'll take O of 1, theta of 1. So now we have to figure out how to solve this. You're going to see a lot of algorithms recursively. We've already seen a bunch in trees. In trees, we've seen a lot of recursion traversals, and you've never really understood why it was O of n, but now we're going to go more into why all those traversals were O of n, or n log n in some cases. All right, so this is our formula, right? So instead of doing this whole complicated thing, we're just going to write it a little bit more simply. This is how we're going to see it from now on. But this is the usual meaning of what we mean when we say this. And when n is 1, it's usually theta of 1, unless stated otherwise. We might say it's something like it's otherwise, or if you have to deduce it from the algorithm. All right. Okay. So we didn't really go into how to solve this. We'll go into that in a second. Okay. All right. Another example. What is the formula for this algorithm? The T of n equals no.
Um, for the n minus one. No, 30 n minus one, I think.
Exactly.
How do you guys reading so?
Okay, they didn't read all of it. What they did is they went, what I assume, unless you guys really did read that fast, they went to the line of code. What does it do? It calls itself on the same thing, and n minus one. So the array shrunk by one, right? So it would be, this line is t of n minus one. Could we call the same algorithm on an input that's one smaller? It would be t of n minus one. Same thing here. It shrinks by one because we move the beginning by one. Also t of n minus one. Here, actually, it's t of n minus two, but and then this line is just, if we get to the end of the thing, what do? And then we return the minimum from all three. So without talking about what the algorithm does, what is the time complexity of the algorithm? So we said before, those three lines are what's important. T of n is t of n minus one for this line, t of n minus one for this line, and t of n minus two for this line. And then the rest of the code is theta of one. Is that understood? Any questions? Nope.
Yes.
Yeah, questions?
No.
Okay. So now that we have the formula, how do we solve it? So like Artem said, recursion trees, recursion trees aren't enough for us to prove what the big O or theta of a formula is, but it's good to help us get a little intuition of what is going to be, and it's also useful in proofs and for other things. But it wasn't in the material last year. I decided to add it because it does really help understand. I don't know how they taught all this thing without recursion trees. That's what everything is based on. For example, t of n equals 2 times t of n divided by 2 plus n. What does the recursion tree look like? At the first level, we're doing n work, right? And then we have two calls. Each one does n divided by 2, right? So now we're going to have two calls, each one n divided by 2. And if I plug in n divided by 2 into our t of n, I get 2 times n divided by 4 plus n divided by 2, actually. But so in each one of these levels and so on and so forth, this is a recursion tree. Now, when do we stop? When do we get to the end?
Oh.
When we get to t of 1, exactly. And when do we get to t of 1 in this case? Log n intuitions, because each time we divide it by 2, that's basically what log does, is it takes our number, how many times do we divide it by 2 in order to get to 1. It's basically what log does. And the height of the tree, like we said, it's log 2 of n. Each level, in this case, if we sum up the amount of work that is done at each level, we get n at each level. Okay?
That's the question.
Yes.
I'm trying to understand. Yeah, I'm not getting it.
All right.
Where's the plus n there?
The plus n.
I'm just wondering how each part of the tree relates to the equation.
So the root is just the first call, right? We call on t of n.
Right.
That's the first call, and each call splits it into two separate calls, right?
Right. It
Of
calls
smaller.
t
So
of n over 2 twice.
exactly. So what is t of n
And we're just
over
ignoring
2?
the fact that there's an n.
No, okay. What he doesn't understand is n in this case is a variable. Okay.
No, I
So-
don't understand.
No, it makes sense.
So you have t of n, and the n in the end is just what you put inside of t. So if you are calling t n divided by 2, n goes to n divided by 2 instead of being n. N is just the name of the variable.
Your n is like a function.
T of n is like a function. So in the first call, we have t of n equals this thing. And that's why we do n at this node. But then when we call it twice, we call it on n over 2, right? And n over 2 is 2 times n over 4 now. And instead of n, we plug in whatever's in here. So we plug in n over 2. So that's why each node now, we have n over 2 at the node. And we do that for the next one, for t over 4 and t over.
But we're
Eight.
ignoring the plus n at the end.
Yeah, the plus n at the end though, it changes. This is a function. Imagine it's like a function that's dependent on n, right? Depends on what we give it here. So if I give it here 8, it'll be 2 times t of 8 divided by 2 plus 8,
Right. Okay.
right? So if I plug in t of n divided by 2, then this will also change to n divided by 2. Well, so will this n, it'll change to n divided by 2.
Okay.
Okay? If you want, come at the end and we'll go over this. It's
And the height of the tree is supposed to be the amount of iterations we have.
exactly if each time we divide n by 2, right? And our stop case, like the what is it called in English? When we stop the recursion is when we get to t of 1. Right? That's when we stop. We know t of 1 equals 1, because otherwise the recursion would go on forever. But if we know that t of 1 equals 1, the second we get to 1, we stop. And then we can go back up the tree. But when do we get to t of 1? After how many times of plugging it in do we get to 1?
And log n times.
Log n. Log 2 of n, because each time we're dividing it by 2.
So then what is the
This is something else. This is basically saying, okay, we have log n levels. Each level, if we sum up the amount of work we did, here we have n, here we have n plus 2, n divided by 2, here we have n divided by 2. If you add these together, you also get n at this level. And at this level, you have 4 times n over 4. So you also have n. So at each level, we have n. We have log 2 of n levels, so therefore we have beta of n log n. Total.
Okay.
Okay? All right. Another example, a little bit more complicated of a tree. Now we have 2 separate calls of one in the different, right? One is n divided by 3, and the other one is 2n divided by 3. So it's a bit different. And how is this tree going to look? Okay, don't freak out. First, we have c of n first level, right? Everyone agrees on that?
Yes.
All right, now we have the left call, which will be a third times c of n, right? Because we plug in this into here, and we get a third times c of n. And here we have 2/3 times c of n, because we just plug in t of 2n divided by 3 will be 2 divided by 3 times cn. Now each one it continues recursively. On this side, we keep on plugging it into the third. We keep on plugging it into here, and this is the left side. And the right side, this right path is just we keep on plugging it into there, and it just keeps on growing squared.
See.
Cn, because that's how they define the function for us. All right, it's Cn. Before it was just n plus n, now it's plus c of n. C is a constant. All right, now the real question. What's the height of this tree?
The height of this tree,
Yes, then this would be less than
it's 1/3, so it's log 3 of n.
Log 3 of n. Log 3 of n, though, is for this side. What
Uh,
about the other side?
oh, right. Sorry.
It's log 3. We also, this is kind of giving it away. But you're right, we have here log 3 of n, and there it's log 3 divided by 2 n. And that's why we have a tree that's a little bit crooked, right?
Yeah.
A little bit of a crooked tree. So this one is log 3 divided by 2 n. All right, why is it omega? Because we're assuming that it's really the log 3 divided by 2 of n, because that's a little bit higher.
Yes.
And we can bound it. We can upper bound it by omega of n log 3. Okay. What is the omega?
It's for the height.
No, it's for the amount of work at each level. Right? We have what?
It's the maximum omega.
Oh, sorry. Omega is the lower bound. Sorry, my mistake. It's not upper bound. It's lower bound. So if we have c of n at each level, right?
Yes.
Once we start not having nodes at this side, we don't have c of n at each level, right? Because it used to be 2 thirds n plus third n, which is a whole n. So we get each when we get c of n. Now we get less than c of n because we're missing this one reaches the n much faster, and then we already lose that side of the tree, so it's going to be less than c of n. So that's why if we do actually take only this part, it's a lower bound because we're not even counting all this part. So it's at least n log 3. And big O also, if we just pretend like it does go all the way, and we really do get c of n at each level, even though it gets smaller and smaller, then we get log 3 divided by 2, n times n. All right, questions on this? Okay. And therefore also it's omega of n log n. That's something that's a little bit harder to prove with the other strategies we're going to see. But with recursion trees, it becomes a lot more intuitive what you're even trying to do. Because if I just give you a bunch of strategies, you don't really understand what's happening behind the scenes. So it's important that I wanted to show you this. So here's another one.
Just go back one more time.
Yeah.
Oh, we're saying it's theta of n log n. It's like in the
Yeah.
middle.
It's like because we know it's omega of n log 3 of n, because if we just cut the tree, we just take only the upper half. It's theta, it's omega of n log 3 of n. And if we take everything, even though we're adding things here that don't actually exist, and we're taking c of n at every level, it's big O of n log 3 divided by 2 of n.
So we can compare that it's theta of n log n
Because it's down upper and lower with n log n. Okay? All right, another one. I think this is the last example of recursion trees. Okay, so this one, now we have c of n equals 3 times c of n divided by 4 plus c and n squared. Now we have c times n squared at each level. So at our root, we're going to have c times n squared. And at each one of these, how much work is happening?
C.
This one, we're calling it
Cn over 4 squared.
c n over squared cn squared over 4 squared, right? We're just squaring the whole thing.
Yeah, I meant.
Okay, all right, yeah. cn over 4 squared. All right. And so on and so forth. The same thing for this. It'll be basically just c n over 16 squared, like this one squared, and so on and so forth until we get to 1. Now, what's the height of this tree? With a little spoiler, but what's the height of this tree?
The 4, the 4, CN.
Because each time we're dividing n by 4, right? So log base 4 of n. Of n, because each time we're starting with n, right? And each time we're dividing it by 4. This part doesn't matter that it's n squared, okay? That's just the amount of work that we do at each level. You can think of this as the recursion calls, and this is like if we would do a double for loop at each recursion call. It's not connected to the tree itself. It's just the amount of work that we do. Okay, back to our thing. So our height is log base 4 of n, and at each level, you can see that we kind of are getting smaller and smaller, and there's a pattern. Right, at the first one, we just have c of n. Here we have 3 times cn squared divided by 16.
Yes.
And then we have that squared at each level. And so we know at each level, we have a specific amount. And therefore, when we sum up all of these different ones,
Like what?
it's the amount of leaves times 1. The amount of leaves is 3 to the power of log 4n. All right. And now to sum up all that.
Oh,
Okay, so you have to sum up each level of c of n, right? Equals c of n squared. Sorry. From I equals 0 to log 4 of n, right? Because those are our levels. And each time we're taking this to the power of I. So at level 1, it's just going to be c of n squared. Right? The equals, we're going to take cn squared out of our equation. Cn squared times our same thing. And then if you did dual geometry, geometric series, you take the sum of the geometric series. That's a constant. So therefore, it's O of n squared. If you want, you can do it afterwards, the math, look up this sum for geometric series. But for now, trust me, you'll be able to do a lot.
1 second.
Yeah.
You do to the power of pi of 3 over 16 because we have 3 branching factors, right?
We have 3 branching factors, and each time it divides by 4.
Okay.
Right? So each time it multiplies itself by 3, by 3, by 3. So that's why it's 3 squared at each level, because now it's 3 times 3, because we did 3 times 3. So there's 9 different nodes. And then it keeps on going. And the divided by 16 is because before we had just 4. And then when we take that to the power, it becomes 16. Oh, sorry, because it's that to the power of something. The n divided by 4 becomes
Okay.
16, and then it continues on. That 16 to the, it just keeps on raising itself to the power. All right. Another one. Okay, this one's easy though. Draw a recursion tree for the function n t of n equals 2 times t n minus 1 plus 1. So this is a little bit of an easier one. How would we do this?
It has a height of n, and you just split it into 2 each time.
Exactly. So first we have 1 at the node, right? Sorry, let's move this more. And that's just there. No. Yeah, get it. All right. So we have 1 at the root, and then it splits into 2, right? Why does it split into 2? Because it's 2 times t of n minus 1. Now each one of these, we have how much work?
And with 1,
No, each one we have 1.
I will have 1.
1, right? Cool, that's a good plan. All right, so each one we have, like, we have 1. Keeps on splitting into 2, and each time does 1. Right? So at level 1, we have here 1, here we have 2, here we have 4. We kept on going. At level I, how many would we have? Here it's level 0, it's 2 to the power of 0.
Yeah, to the
Here
power
it's 2 to
of
the power of 1, with 2 to the power of 2.
Yeah, to the power of 5.
2. At level I, we have 2 to the power of I. Okay? And now what's the height of this tree?
And
N, exactly. So what's our final analysis?
so it's 2 to the power of 5 plus the 2 to the power of 10 plus 1. Yeah, minus 1.
Big one up. I equals 0 to n minus 1, I believe. Of what?
Of 2 to the power of 5.
Exactly. Exactly. So we're summing up 1 plus 2 plus 4 plus so on, which someone help me.
N times n minus 1 over 2.
N times.
I
It's
think
just like some of geometric series. I don't remember by heart.
Yeah.
But
Well,
it's the factor. I don't remember it exactly, but the first element times whatever, something, something, something.
it'll be 2
to
to
the
the
power
power
of
minus 1 minus 1.
No, just 2 to the power of 10 minus 1 and then minus 1. Yeah.
To the power of 10 minus 1.
No, and then minus 1.
Or then minus 1 divided by.
And then
You have it?
and then just 2 minus 1.
You have it?
No, it's the other side. No, this is the other way around.
And then
Wait.
Guys, imagine it in the binary expression.
It's what?
I know. No, the final result. The final
The
result.
final result, yeah.
It's what they've been saying. It's 2 to the power of n minus 1 minus. No, 2 to the n plus 1. Plus 1.
But it goes until minus 1. To the power of n.
Minus 1.
Minus 1.
No, minus 1 in the power and the
And then
minus 1.
Yeah.
Minus
No,
1?
Yeah, that's what I'm saying.
No. I agree, we're gonna check this out.
Now imagine it in the binary.
You need the
expression
sum.
of a number. Zeros and ones, by binary number, right?
Uh-huh.
We got all the ones. We
But
have
this can't be, you know why? Because if the last element in the sum is 2 to the power of n minus 1. and we're adding more number. We're also adding 2 to the power of n
No.
minus 2.
Imagine this sum in binary representation. We got n ones. It's just a number with n ones.
Mhm.
What's
Okay.
the binary number with n ones in the decimal representation?
N ones in decimal.
Yeah. So in
I
binary it's
understand.
n ones. In
Okay.
binary it's a number with n ones, so that's all it has. Then we convert it to the decimal. What is what it would be?
Right.
N minus one. Okay, n minus
I have to continue, but I want to understand afterwards. Okay, I don't want to understand. I just have to continue.
This is
I'm gonna do it afterwards. I'm so sorry, everybody.
right.
Either way, it's okay. Either way, it's a big O of 2 to the power of n. Does everyone agree with that?
Well, no.
Oh wait, no.
Yeah, more or less.
Whether it be 2 to the power of n minus 1, to the power of n, it's still O to the power of n.
No, alright.
Okay. Alright. Alright, we're gonna continue on, Thomas. We're gonna go to afterwards, okay? If we have time at the end, because we have a lot to get through today, and I don't want us to be behind. Okay, iterative method. Now we're gonna go through some methods that are not recursive trees. Instead, we can do something else. Alright, I'm sure you've done this in Intro to Computer Science when you had to analyze recursion functions, but we'll just keep on substituting our function again and again. We'll just continue substituting it within itself until we get a general formula, and we'll prove our general formula and find our big O. So let's give an example.
So are there times when it's better to use the previous method than that method than this method?
Yes, whenever it's better for you. We can go over, yeah, it's whatever's easier, but there are certain things we'll go over. This is better for when you have n minus something. This one's not good for if you have n divided by something, but it also can work for that. Whatever. It's whatever is more comfortable for you. If it works, it works.
Okay, fine. So I
Okay.
really don't like the other method. I don't understand
Okay.
that.
Okay. All right. I would go over that because it is important, but okay. So you just substitute t of n. We want to take this part and substitute this, right? So what are we going to do? We're going to substitute t of n minus 3. We're going to plug it in, and then we're going to get 2 times t n minus 6 plus 2. All right, we just plug this in. And then we're going to just open up the parentheses, and we get this. And now we're going to substitute t n minus 6, and we're going to get 2 times t n minus 9 plus 2. We're going to open it up, and we get this. So therefore, at the depth of I, what do we get? The you see here, it always raises itself to the power. So it's 2 to the power of I at each level. Here it's minus 3 times I. And here we have a sum of geometric series again. All right, so we get 2 to the power of I times t n minus 3I plus the sum of the geometric series equals 2 to the power of I plus 1 minus 2. And this actually answers our question from before, that it really does equal 2 to the power of n minus 1.
No,
We're still debating.
series though.
It's a different series, but it's still the same. 2 to the power of something.
No, but
From j equals 1
j is equal by
to 0. You're saying because it's 0, it's different?
Or should it? It's uneven, but that's even.
I think it doesn't matter, but we can go over it afterwards.
Okay.
Or you're saying because it starts at 2. Okay, maybe.
That's uneven.
Maybe.
Yeah, that's even.
We'll go over it afterwards. All right, so now that we have our guess, this is our guess, all right? We iteratively go and substitute our function, and then we take an educated guess on this one. But you could be able to be wrong. There's cases where it gets complicated. So in order to prove it, we prove it with induction. I know you guys missed induction.
Actually, missed me.
Oh, all right. So we want to prove that for every I until n divided by 3 minus 1, because that's how far the recursion will go to. If we go back to our function, right? How many times does this call itself? N divided by 3 times, right? Because each time, sorry, not n divided. Yeah, n divided by 3. Yeah, n divided by 3. Okay. So let's prove the induction for I equals 1. The base case we'll get if we sub in 1, it's just all i's become 1, which basically just equals our definition of the function. And now we're going to assume for I equals k minus 1, and we're going to prove it for k. A lot of arithmetic, but all right. So t of n equals 2 to the power of k minus 1, n minus 3. Basically, just here what we did is we just plugged in k minus 1, right?
Yes.
And then what we did, why did we start with k minus 1? Oh, okay. We start with k minus 1 because we didn't get to t of over 1 yet, right? T of n equals 2 to the power of k minus 1, t n minus 3, but it's 3 times k minus 1, the amount of times we did that. All right? And then that's plus that amount from the induction hypothesis, which equals to 2 to the power of k minus 1. And then we're just basically here opening up the parentheses. And then we transfer from here to here is that we have 2 times this thing. We basically just did this one more time. Right, the induction hypothesis, we open it up k minus 1 times. We substituted it k minus 1 times. This is what we got. Now if we take this whole thing and we substitute this with our function again, we get 2t n minus 3k plus 2. Because this minus 1 just goes out. And it's hard to do without me doing it on the board, but you have to trust me that if you take if you take this, the t of n, and we do it one more time on that step. So I'm really not explaining this well, but it's some hard transfers. So from here we basically use, this is just the induction hypothesis. We're assuming it for k minus 1, right? So we substituted it k minus 1 times, and this is what we get. Now what we do is we substitute it one more time. Okay? We substitute it one more time. I'm not going to go over all the different opening parentheses because it's making me crazy. But this is what you get when you substitute it one more time, is that it goes from t of this whole thing to 2 times t to whatever the formula was. Now we take the 2 out, it's to the power of k, and then it's just simple arithmetic, and we get to our desired induction hypothesis. All right, so we proved that this, right? But now we still need to get a big O. We still need to get a theta. So what do? Let's say it's usually given that t of 1 equals 1, but here we're told that we get t of 1 and t of 2 and t of 3 equals 1. Therefore, if we substitute I equals n divided by 3, because then we'll get to 1 of these at least, we'll get this. T of n equals 2, and now we substitute I equals n divided by 3.
Why?
Because in our general one, this is our general one, right? So we want to substitute something that'll make t of whatever this is. You want this to be 1 or 2 or 3 in this case. We want it to be t of 1. How do we make it t of 1? If I equals n divided by 3, what does that mean? That if I substitute this times, like n divided by 3 times 3 is n. N minus n is just t of 0. But if you wanted, you could do t n divided by 3, like minus 1, to get actually t of 3. But you want to make what you're trying to do, trying to make t of whatever this is equal t of 1.
Okay.
Get it to be equal to this thing. Okay? Alright, so now I'm substituting so all these 2 to the power n divided by 3 times all these different things. Basically, this and this are basically the same. It's just the theta of 2 to the power n divided by 3. Alright. Moving on. Alright, we want to find with the help of the iteration method a type bound for this function then. Alright. So you're going to help me. How are we going to do this?
Oh man, I can get through it. I want to get through.
You're gonna save some process time. I mean,
Okay.
square root of n is a pain in the ass, but like.
Okay, so we're going to do it verbally. Ready? How do you start with the iterative method? Sammy, how do you start?
You plug in the t of n and through n into that.
Exactly. So you plug in the root n, right? So you get 2 times, and then in parentheses, now we have 2 times t.
Up to the 1/4.
Yeah, basically the n to
1/4.
4 of plus 1 plus 1, and then you continue so on and so forth until you get to a formula, right? You get to this probably being 2 to the power of I times t n to the power of 1 divided by 2 to the power of I. I think it's plus 1. But either way, plus, and then the same thing, the sum of I equals 0 until so j equals 0 to 2 power of j, right? Because this one is going to become now 2 times this, so it's going to be 2. It's going to be 1 plus 2 plus 4 plus 8. So this time it's going to be. And I'm going to get this thing, and we're going to do the same proof.
No, it's gonna be the next one's gonna be 3.
What do you mean next one's going to be 3?
The next one's gonna be 3.
No, it's not.
It is.
Why is it going to be?
This is
There is 1, right?
One
And
plus
it's here, it's
plus.
inside the parentheses. So what's this one? It's not actually 1. If I took it outside of the parentheses, it would be 2.
Yeah, so 2 plus 1 is 3.
Yeah. But then the next one, what would I get? 2 plus 1. I'm just going to write it out like this instead. Okay? The next one, if I substitute it again, I get inside, I get plus 1, right? But it's inside this already. So it's 4 times 2 times 2, so it would be 4, right? And then it'll be 8, and so on and so forth. And that's why we get to this thing. Okay? You can go over the previous example. It's the same exact thing. If you want, you can do this fully at home. Then you have to prove with induction, and so on and so forth. All right. Little Tim's happy right now. She's really enjoying this. All right, substitution method. Method's a bit different than the last one. Technically, the last one could have been called substitution method, but they decided to call it the iterative method. This one is a bit different. It's basically a guess. We're going to guess what the big O is, and then we're going to prove it with an induction. Okay? So we can't prove theta. We have to prove upper bound and lower bound separately. So let's say for this function. It's a very common function, right? We know this. What do you think this is? What big O? N log n, right? You know, if you know Master's theorem, we're going to go over that in a second. But it's basically O of n log n. So first, let's say we guess too high. We know it's n log n, but let's say we guess too high, and it's O of n squared. And we're going to prove that it's within O of n squared with induction, right? There exists a C, blah, 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 blah. Right? So we're going to prove with induction, T of 1 is very simple. 1 is smaller than C times 1 for every C that's greater or equal than 1. Now we're going to assume that the claim is true for every n smaller than n, in particular for n divided by 2. And then we're going to prove for n. All right, so now t of n equals, we're just gonna plug it in once, all right? We're just gonna plug it in once. 2 times just basically our whole function. And then we know that Tn divided by 2 from the induction hypothesis is O of n squared, right? There exists a C such that T of n is smaller or equal than T times n squared. So we're going to take this whole part and just plug that in. We know that by induction hypothesis, it's smaller or equal than some sort of C. And then the rest of it stays the same. And then now we have basically just C and you open up the parentheses there and plus n, which is smaller than equal to then if I would have taken this twice, which is smaller or equal to C times n squared. And we've therefore proved that it's within big O using induction. Any questions on this? It's not the what? It's not the right answer, right? It's not a tight bound. It is an answer. It's not a tight bound.
So get the frequency.
Here's the right answer, it's just not the best answer.
You can prove it for omega. Right? You can prove upper bound and lower bound. We're not doing that here. We're not doing that as an example. Here we're just proving for big O. Yes, look at and on the test, homeworks, no?
Yes.
If you want to prove it with it, you have to do the lower bound too. Okay? If you want a theta, if you want to know that it's the right bound. It's not a tighter bound, like you said, it's not the right bound. We can try that it's to guess that it's n log n, and then we'll prove the same thing using induction. So first we're going to fix n0 to be greater or equal to 2, because we're going to need that information soon. So the base case t of 2 equals 2 times t of 1 plus 2, which equals 4, which is smaller or equal to c times 2 for every c that's greater than 2. All right, assume it. So that's our base case. Now assume it holds for every n smaller than n, in particular for n divided by 2. And then we're doing something very, very similar. We're going to do the same thing. With the induction hypothesis, we're going to just sub that in, right? Just instead of Tn divided by 2, we know by the induction hypothesis, this is smaller, equal to C times our function n log n. So we just plug in instead of n log n, it's n divided by 2, log n divided by 2, plus n. And then we're doing a bunch of little tricks that we're basically splitting it to this just basically log n times half. So we're adding this whole thing. Also, the 2 cancel each other out. So Cn log n plus Cn log half, right? Just a multiplication trick plus n. And then we just get that whole thing, which is smaller or equal to Cn log n. And then we've proven that it's within big O and log n, and we know that that's the best. But if it was on the homework, you'd have to do also the lower bound, which is the same thing, just reversed.
Log of half is -1.
Log of half is -1, yeah.
No,
It's log
no.
base 2.
It's
log base 2.
Yeah, it's divided by 2. That's why it's.
Yeah, it's log base 2. 2 to the power of what equals a half? -1. Okay, so for our example, we still need to choose for the induction hypothesis. We're proving the step of the induction. We still need to choose C and n is 0. We said we fixed it greater than 2, but we have to now really choose this. We'll choose n0 equals 2 and c equals 3, and this holds true for those.
It's log of half, log of 0, log of 1 minus log of 2, which is 0 minus 1.
Log of 1 minus log of.
No, yeah, log of 1 minus log of 2, which is 0 minus 1.
Yeah.
Does it show that?
What, that here?
Yeah.
Where do you have log of 0 log of 1 minus? Oh, here.
Yeah.
Oh, you're saying log of half. If you take log of half, then yeah, then it could also do that. Yeah, that's also -1. What I want to, if I would have written this, so I didn't write it, I would have just done, it's just log of n minus log 2.
Yeah,
That's what I would have done.
Yeah, because
Same thing.
log of half is like.
This is
zero,
valid.
zero
That's
plus.
valid, yeah. This is kind of confusing. When I saw it the first time, I was like, why is it not minus here? But okay, another example. for the formula, this formula, we're gonna guess. This was a little bit harder. You don't know what this formula is, right? Before we knew it was n log n. Now we don't know. So we'll guess. We'll guess that it's O of n. If you want, after in the master theorem, I can show you why it's basically. If you want, you can say this isn't formal at all. It might help you with the guess though. But if you have t of n divided by 2 plus t of n divided by 3, you can kind of combine them. You can say this is smaller equal to t of 5n divided by 6. Right? I just added these together. And you know that's less than 1. So if it's less than 1, we're in case 3 of the master theorem where this is the bigger one, and that's why it's O of n. If you didn't understand that, it's all good. Okay, so we're gonna do the same thing. We're gonna prove by induction the base case. Assume the claim holds for all n smaller than n, in particular n divided by 2 and n divided by 3. So now we're gonna use, just substitute it once. And the same thing we're gonna do use the induction hypothesis, smaller or equal to c times that same thing. And then just substitute open parentheses smaller than c of n. And then you have to say it holds for a specific c. If you would use a c that's smaller than 6, it wouldn't work because then this wouldn't, this inequality wouldn't work. If you didn't take a c that's bigger than 6. All right. That's the other example. All right, substitution. Wait. Is this the substitution? Okay. So this is an example that we're not going to do because I have to do it on the board. And I want to continue onwards. But it's also the same thing. You'd have to prove it. You'd have to make an educated guess, prove with induction, and then find the C and N0 that hold that step of induction. We're going to continue on if you want. It's a good problem to solve at home. This one's a very good one. All right. Okay, Messer theorem. I've thrown this around quite a bit. Here it is. So if you have formulas only in the form of a times t n divided by b plus f of n, then what you can do is you can use the Messer theorem. If we had the formula like we had before, where it was t of n divided by 2 plus t of n divided by 3, you can use the Messer theorem because it doesn't fit the exact requirement. Okay, so you guys have all seen this from Intro to Computer Science. Now, what is that little epsilon that's following us?
Because we want to be strictly less.
Exactly. We want it to be, for big O, we want it to be strictly less than, we want this to be strictly less than this. So it has to be for some epsilon greater than 0. It could be 0.5, it can be 0.0001. But this epsilon has to be something that's greater than 0, that this still stays bigger than this always, right? No matter how big the n, and that it's polynomically bigger than the other one. Yes.
Why don't we just say a small O and without epsilon?
It's a good question. I don't have an answer.
Okay.
I'll look into it. If you want to, we can look at it after the lesson. But it's a really good question.
Then you could choose
Oh,
anything.
because I think big O, if it was little o, it's not, it's even stricter than what this is. This is, we want it strictly smaller. I'm just thinking like generally it would be super strictly smaller, right? Because for big O, you need for every single constant C, you need to find an N0.
Yeah.
Right? So it's a lot more strict, and we want it to work for like, if it's even a little bit polynomically like bigger.
Okay.
I don't think it would work with little o, but we can sit on that afterwards. All right, so I decided to add this. What's the, Sammy's gonna hate me for this. All right, what's the idea behind the proof of the master theorem? Basically, we're gonna go through recursion trees, right? So now this is our formula, right? We have f of n as the root. Then each function call we have a different calls. Right here, I just drew two because I didn't know how many to draw, but there's a amount of function calls, and each one is f of n divided by b, right? Because now we're substituting in here n divided by b, so therefore it'd be f of n divided by b. Sorry, this is also not completely correct because it would be f of n divided by b inside the parentheses. That's my mistake.
So wouldn't that be a lots of it?
What? There should be a amounts of it. You're right, though. Here I decided it was 2 just for the drawing, but there's a amount. Same thing for the next one. The next one, again, ignore that the bi is not divided by within the parentheses. So what's the height of our tree?
Log B.
Log b of n, exactly. Our height is log b of n. And how much work is done at each level? What's our first level? How much work? F of n. You just do f of n. And the next level, how much work do we do? F of a times f of n divided by b, right? Because each one we do f of n divided by b. And there are 8 of them. Here there's only 2 in the drawing, but there's actually a. And so far, and so on and so forth. And we have a squared times f of n divided by b squared. And at level I, we have a to the power of I times f of n divided by b of I. So therefore, the sum of all the levels is what? Well,
C.
is a sigma t of n equals a sigma from I equals 0 until h minus 1, right? Of ai times f of n minus divided by bi, plus at each level, we do theta this amount.
Y. A.
Why it's n to the power of log b of a. Second, because no.
What was the question?
Why is it log n to the power of log b of a?
Yeah, because you switch it, right?
I think I skipped something.
What does plus mean?
Plus
Yeah. Plus that one.
plus the theta. That means. Is this a mistake?
No,
No.
it's not a mistake.
Some of the work we do at each level, right? But why plus this? I think it might be a mistake, no?
No, it's factor instead. Because it's plus log B of n.
Yeah, no, but yeah,
Log B of n is like log.
I think it should be equals and not plus, so that's the mistake.
Oh, maybe that's the mistake. Because there's nothing, there shouldn't be anything.
Plus and equals all the same t, right?
Yeah.
Okay, let's continue on. Maybe it'll become understood afterwards. Number of leaves is a to the power of h, right? Each time it splits to a different, each node splits a times. And to the power of h, the amount of levels. And we already said there's log b of n, the amount of levels. Then logarithmic and power levels, we switch the a and the b. Therefore, the sum at the leaves is, well, O theta of, I don't know why this is here, but equals n. This is the amount of leaves, right? Times O of 1, theta of 1 at each level, which is theta of n to the power of log b of a, right? That's the amount of work we do with the leaves. Okay, why is this important? Because now we want to know, in the master theorem, we compare the root to the leaves and to the internal nodes, right? So what is case 1? Case 1 is this, right? You compare f of n to n to the power of log b of a minus epsilon, right? So therefore, f of n is smaller than this. And what is this? What did we say this was? It's the amount,
The last layer.
the last layer, right? So basically, we're saying that this, it's we can ignore it relative to this because this is so much bigger. So therefore, we only take this in the master theorem, right? So we only take the leaves. And case 3 is the same thing, but all the way around. The root dominates, right? Because each level it'll get smaller and smaller and smaller. So f of n is a lot bigger than this. Then each level we're doing smaller amount of work and smaller amount of work. So therefore we're only going to take the root because that's the most amount of work we're going to do. So therefore it's theta of f of n. And case 2 is that we sum the same amount at every level. So therefore it's the theta of each level times the amount of levels, right? Times the height of the tree. Okay. All right. So basically, that's what the idea behind the master theorem is. That it's just recursion trees. That you compare the root to the leaves. If the root is stronger, then you take the root's value. If the leaves are stronger, you take the leaves value. And if they're the same at every level, you times it by the height of the tree. You work at every level times the height of the tree. Just a little thing I thought I'd add in. All right, so now using the master theorem. Find a tight bound for the formula T of n equals 8n divided by 4 plus n squared.
They are equal, so it's case 2.
They're equal.
I know they're not equal.
Wait a minute. Yeah, because it's log b of a, right? It's log b of a. So therefore it's 1.5, because 4 to the power of 1.5 is 8. Tricky, you almost got me. No, you did get me. But
So this is case 3.
exactly. So we're in case 3. That which one is bigger, the root or the leaves? The root. Yeah, exactly. Very nice. So therefore, we compare them, and epsilon can be anywhere from here to here. We just need to find a epsilon. We don't have to show obviously for every epsilon, just for some. So therefore we're in case 3, and that's why we're in theta of n squared. That the root is the biggest, so n squared is the biggest because each level we get less and less and less. All right. Find a tight bound for the formula. This formula. Now, which case are we in? Log 5 of 4, which is greater than less than 1. This is n to the power of 1.
It's no, it's not greater.
It's less than.
It's
Oh, sorry. My bad. It's log 4, right? Log b to a. So it's greater than 1, and therefore we're in case 1, right? All right. So like we said, what? Yeah. Here it's 2n, but why is it case 1? Because now, which one is bigger, the root or the leaves? The leaves.
N.
2n, but which one is bigger? If n is really big, which one is bigger asymptotically? 2n for n to the power of 1.161. N to the power of 161. All right, so exactly. So it's n to the power of this, Right, because the leaves dominate. Okay. All right, find a tight bound for the formula. This is the last formula. Which case is this? The only one we haven't done. Log base 3 of 9 is 2, therefore it's the same, it's within theta, therefore we're in case 2. And then we do the same work at every level, we do n squared at every single level, so therefore we have the height of the tree times n squared.
Aren't we missing something for the case 3? There was another condition.
Case 3 or case 2?
Case 3.
Right now we're in case 2.
I know.
Is that-
We already did
okay.
3, right?
We did 3,
I
yeah.
didn't check the condition.
Which condition?
For case 3, there's an additional condition that we need to check.
Which
We need
one?
to check it.
Which condition? So case 1.
I don't know if it's stated on the board, but it definitely exists.
What's the condition?
I remember.
Oh, there's another condition you're saying.
But no, there's 3 cases, but for third case, if this is true, what third case says, then you need to check another thing, and it's possible that like Master's theorem doesn't work at all.
Okay.
AF of n over v should be less than KFN for some k over 1.
Okay, let's start.
Less than 1, sorry.
Yeah, that thing.
What is it?
That
Regularity condition A.
It's okay. We won't also demand this.
it wasn't a lecture, right?
For what?
It wasn't a lecture.
It wasn't. It wasn't a lecture.
Yeah.
Okay.
Wait, I will check.
Condition.
Where's so
And did he tell you why?
I didn't show the theory.
Can I see it again?
No.
Oh, come on. F so n over b.
Will be less equals
Is equal then.
KFN or some k less than 1.
Did he tell you why or no? So I'll go over it afterwards.
He didn't explain it enough.
He didn't explain it?
Just
Okay.
did the pieces.
Okay, so that's another condition then that you'll have to use. All right. The master theorem is definitely the simplest. Very easy to just plug it in and do that. All right, last one is variable substitution. Here, what we're gonna do, we're gonna look at the formula. And now this one's kind of complicated to do, right? It's a little more complicated. It's square root of n plus log n. We can do it with substitution. It's kind of complicated. Sorry, not substitution. Either substitution guessing or iteration. We can just iterate and substitute it I amount of times. But here we're going to use a different trick. Here we're going to denote m equals log n. Therefore, 2 to the power of m equals n. And now we're just going to plug that in to our formula. Now we're going to, instead of m, n, we're going to write 2 to the power of m. And we're also going to plug that in for here. It's square root, so it's to the power of half. So that's why we get that. And log n equals m from how we defined it. So therefore, this is our new function that is dependent on m. Now we're going to do another trick that s of m equals here. We're going to basically denote this to be equal to this, right? So now we're going to solve s of m. It's going to be very simple. And then we're going to substitute all these things back in to get our actual data. So now s of m equals 2 times s of m divided by 2 plus m. And the solution of that is very simply m log m, master theorem, whatever you want. We all know this. We all know this one. And now we're just going to substitute it back in. Exactly, we're going to substitute it back in. So now t of n equals t of 2 to the power of m, which equals s of m, which equals theta of m log n. And then we substitute m for log n. And then we have log n times log n, which is kind of hard to do with the substitution or iteration. Therefore, we need the variable substitution. All right, another example, new formula. Now instead of plus log n, now it's plus 1. So we can do the same exact thing. Denote s of m, and now s of m equals s of m divided by 2 plus 1. Master theorem is just log n, right? I don't wait, why is it case 2? It's log 2. Log base 2 of 1 is 0. So that's why it's the same, right? In master theorem, now we want to compare the b and the a, right? Log b of a, log 2 of 1. Therefore, we get 0, n to the power of 0, and this is also n to the power of 0. Therefore, we get just 1 times log m. And therefore, we're going to substitute it, and we're going to get s of m equals theta of log m, which equals to theta of log m.
You go back to the previous slide.
What?
You go back to the previous slide just for a second.
Okay, if you want to read more about these different methods, there's in the book. All right, now we're going to do as much as we can from the next one. All right, divide and conquer. You got what you guys did in the lecture. We can do some more problems here. So first off, divide and conquer. It was here. I wrote this for myself. In the picture, Philip II of Macedon. He's the one who quoted the divide et impera, which is divide and rule. It's attributed to him. That's why there's a picture of him. I just had to look that up because I'm a history freak. All right. A paradigm is a pattern of thought in a scientific field, or similar. That word context. That word basically just means study of knowledge from philosophers. You can look. There's a Wikipedia page. All right. So what does that mean for us? In algorithm design, a paradigm is a particular method, way of solving it, right? It's a specific approach to solving an algorithmic problem, right? And it can be useful for solving a lot of different problems. So therefore, when you teach this method, which divide and conquer, just like it sounds, we're going to divide our big problem to a lot of little problems recursively. Then it's going to be easy to solve. We're going to sum it back up, and then we'll get our solution. So we're going to learn 3. Sorry, I didn't fix it because this wasn't in the course, but it's going to be in the course this year. It was also in last semester. So we're going to have divide and conquer, dynamic programming, and also greedy algorithms. These are all paradigms of thinking, of approaching algorithms that you guys will have to know, and we're going to go over. All right. So divide and conquer paradigm, it's an algorithm that operates in 3 stages. We divide, we solve each individual problem, and then we combine, like I said. Not necessarily in this order. Sometimes we do it in other orders. Most of the time it's in this order though. Example, sorting and merging, right? We didn't go over sorting yet, but that's the algorithm we saw in the recursion formulas. It's the merge sort, where basically we divide the array into 2, and we keep on dividing it into 2 until we get to just one element, and then we plug it back in. Okay. So separate, dividing the array into 2 parts, and then we have to merge. Basically, we sort each half of the array, and then we merge the 2 sorted halves into one whole sorted part. So in not analyzing these algorithms, you have the recursion calls that you have to figure out how many are done, what the recursion formula is, and then you also have to figure out how much work is performed at each level. So if your array is of length n, what's our work that we're doing here? If we have to merge 2 sorted halves into a whole, that's O1.
That's
Okay.
Oh, and because you have to make a new array?
No, because you have to go through both of these halves one by one.
Oh yeah, you're right. Completely right. So it's O of n work. Quick sorting.
Isn't it O of n over 2, which is still n? Okay.
No, it's still n because you have to go over all the elements.
It was a half though, so it's exactly.
All right, quick sort, you separate and combine. We're gonna go over sortings and the sorting recitation. Okay, binary search. Do you guys know what binary search is? It's if you have a sorted array, right? You have a sorted array. Exactly, we start from the middle. If I'm looking for the element 257, I look at the middle. If the middle is greater than 257, I know it's in this half. If it's smaller, I know that it's in the bigger half. And I continue on recursively until I find my element. So we divide, we treat the arrays as you have a median, smaller half, and a larger half. That's our divide. Combine, we compare our element to the median. And then we determine which side is located, and then we match. We find it recursively in the half of the array. So how do you implement this? I mean, pretty simple, pretty straightforward, right?
Yeah.
All right. Okay, now we get to questions. Rising and falling array. Given an array from 1 to n, such that we know that there exists a k, such that the array rises in the first k cells and descends after that. So therefore, we're going to get something like this. We're going to have an array of an element where all the elements are there's gonna be one place where everything descends and everything descends on the other side. Okay, that's just formally for every I, it holds that AI smaller than AI plus 1. It's the first half, and then this is second half. That it grows in it, well. Okay, from now on, we're going to try and describe algorithmic problems by input and output. Instead of saying, given blah, 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 find this. Instead of that, we're going to try doing input output. So what's the input for this? It's an array. No, same thing. And the output, we want the index k. All right. So how do we do this?
The naive approach would be just to go from the first element until we find the first element that goes down, and the one before it is the answer, right?
Where you just keep on going.
Yeah, until you find
Yeah,
someone.
that would be what O?
Oh, then the worst.
Well, then at worst case. And what's another solution?
Start from the middle.
Yeah, like binary search, start from the middle, right? And then check its two neighbors, and then it'll tell you which side to go, right? So that's what we're gonna do. Okay. So we're gonna identify the middle, like we said. Okay. If the middle index is k, that its neighbors are both smaller than him, then we return k. If it's less than k, we'll solve recursively on the right half of the array. And same thing the other way. If the middle index is greater than k, we will solve recursively on the left half of the array, right? Okay, fine. K, here's the pseudocode. Now, an important point about pseudocode that I didn't say. A lot of people, maybe you guys didn't, but a lot of people have asked me what constitutes pseudocode in this course. So all that we want is it's an outline of code where you do cover all of the edge cases, but it doesn't have to be written in a way that's going to compile. It just has to be very understandable how I could turn this into code. That's the criteria. We just have to be able to turn this into code very easily. Yeah.
In homework, I just showed a C++ code and screenshot that works.
It's technically code that's not pseudocode.
Thing, right?
There's not pseudo on that code.
Listen, I'm not checking the homework, but I'm assuming they'll give you the points.
It's playing English hands right now. You get a 0, you say it's original.
I'm assuming they won't take it off, but if you can appeal, and I'll send me an email.
Okay.
All right. Okay, so this is our algorithm. Basically, find k. We have our array. We have the beginning and the end. If beginning and end is, I don't know. I think it might have been in the translation. I don't know why there's a 3 there. Okay. I don't know why there's a 3 there, but this is our edge case, and then we set m to be equal beginning and end divided by 2. This is our median, and then what we just said verbally, you have to write in code.
I think it's supposed to be like less or equal to 3.
It's supposed to be less than or equal to 3. That makes more sense. Yeah, if it's less or equal than 3, then just solve it, right? It's probably if it's less than 3, there's no median, right? You just solve for 2, right? You just go over both elements. And you find the biggest one. Okay. Now, you'd find the median if the median minus 1 is smaller than our median. And also our median is greater than, but it's after it, and we found k. Return our m. But if m minus 1 is smaller than m, then we'll just repeat recursively on the latter side, right? Because if the one before is smaller than the one after, then we know that it's somewhere here, right? Because we know it grows bigger and bigger and bigger. And else we know it's actually the other way, and we have to go to the right side. We go back to the example. If we're here, right, we know it's not k because both of the sides are not smaller than it. So we go to the side that's bigger, right? So we divide it to this half of the array, if like we were divided it in the middle. And if we're over here, then we go to that side of the array. All right, what's the runtime of that?
Low.
Well, you gotta use.
Yeah.
You're right, but you have to show me with the recursion formula.
No problem.
No problem? Okay, all right.
Very nice problem.
Well, what?
Take a picture, show your parents.
All right, another question. Yeah, maybe we can get through. Okay. We have a densely populated neighborhood and a little bit of rain falls. Now we have an array that basically represents the buildings. So there's actually a great picture here. We have an array that represents the height of all the buildings, and we know that the rain falls and lands on the roof. If it has somewhere to go, if water has somewhere to go, goes down as far as it can. So if water rains here, it'll go to the side. Water rains here, it'll split to both sides. We want to find a place where here I'll show you the input and the output. Puddles only form on roofs that are lower than both of their neighbors. So here there would be a puddle. Okay?
So this is like our question for inclusivity.
It could be. Okay, input the array of building heights, and the output is any building on whose roof a puddle will form. We can choose anyone. We can return this one, we can return this one, we can return this one, doesn't matter. We have to return one of them. Also, I didn't say this, but if you have, let's say this is like our array, then this is considered a puddle. The edges are considered infinity. Okay? So therefore we're always guaranteed that there's at least one puddle, because otherwise.
And the water falls everywhere.
Falls, yeah. It just falls down. It goes to the left or to the right, whichever one's smaller.
I mean, I don't see how this could be better than often.
You know then?
Yeah.
Let's try.
Nice.
Oh shoot, I let it go.
Yeah.
I was
Yeah.
I'm on a weed war on mosquitoes, just so you guys know. Okay. I'm trying so hard not to sweat. Okay, whatever. Okay, describe an input for which there is no answer in the left half of the left, in the left side. In the left half.
Sure.
So
And monotonically
Decreasing.
decreasing, yeah.
exactly. Monotonically decreasing. Then we know that on the left half there's no solution, there's no place that we can get a puddle, because even though like this one is far on the other side, there's no one that has both of the buildings all in it. But we're guaranteed that there's an answer on this side. Yeah? Alright. So now how are we gonna solve it? Obviously with divide and conquer, because that's what the recitation is on. But how are we gonna solve this?
Well,
Yes.
if it's not this case,
Mhm.
then like the first one is gonna have a bottle.
The first one's
Yeah,
gonna have a what?
the
A
bottle.
puddle.
Okay.
What's the first one? Oh, the first one.
Yeah.
Oh, you're saying like in this case, this one's gonna have a puddle.
No, if it's not this case,
Okay.
the most left one is gonna have a bottle. And if it's this case, we do a binary search.
It's like this, but
So we're gonna do binary search. That's the solution. I didn't get if it's not this? You mean if
Like if let's consider first and second building.
like this?
Yeah, so let's just consider first and second building. If first is lower than second, then we just output the first one. And
Exactly.
if the first is higher, then we do binary search
Okay.
until we find the.
You mean if the first is higher, exactly.
Yeah.
But you don't really have to do that necessarily. There's a good chance that you have in the first couple you'll have a puddle, but you don't have to check the first
No,
one.
but
We're just gonna do.
Want to do the binary search that searches for this thing, right?
Mhm.
Where the left one's higher, right one is higher as well.
Oh no.
And flaring in the starting point for the binary search.
Yes, just choose
Oh,
another one.
no.
Oh no.
What happened? Yeah.
Oh no, I had the video on. I don't know when it turned off, but it turned off at a certain point. I'm hoping that it's now when it just told me. I'm hoping. Let's pray. You guys pray for me? All right, let's finish up this this question and then we'll be done for the day. Okay. So I'm just gonna go through the answer. But you were right, Artem. We do binary search. Okay, we're gonna look at the middle building. If it's lower than its two neighbors, we're done. Right? If it's not, what we're gonna do is we're gonna check its left and right. If the building to the left is lower than it, we know that there's a puddle on the left side, right? It's kind of like we did before. If we take this, let's say, we don't know, there's not guaranteed for us that there's a puddle on that side. But on the lower side, we're guaranteed that there's a puddle. Okay? So we're gonna look at the lower side and we're gonna take that half and operate recursively on that half of the right. Otherwise we'll solve on the other side. If we continue to a certain point, the call is the exact same problem.
Wait, you just want to find one puddle?
We just find one puddle.
Oh,
Yeah, just one puddle. That was the output. Okay.
That's why we're getting confused.
No, I thought it was like all the puddles.
No, just one puddle.
Okay,
Just one
that
puddle.
makes it way easier.
Yeah. That's why it's very important to read the input output. A puddle is somewhere where the water will gather, right? That both of the buildings. Puddle's just to imagine.
It's a
So
little
little lake.
called this.
It's a little
Word?
little lake.
Schlulit. טוב. אז הנה, נגיד פה, sorry. We go to the middle, right? We go to the middle element, and then we go to, if this building was taller, we define a puddle, we return it. But because this side is smaller, we'll recursively operate on that side. So we take the middle of here. And the recursive call this element shall only be compared to the neighbor. Okay, so because we already, this is an important point, that we compared 5, right? Technically, we went to the lower side. So we don't have to keep 5 in our array, because we don't need to check 5, right? And we know that 6, you know how the edges have basically infinite? So we know that 5 is bigger than 6 because we went to the lower one. So we can operate recursively on this. When you break it down to divide and conquer, you have to show that the recursive calls still operate in the same way, right? Because if it's something else, if it's different, if it changes the whole problem, you can't actually operate recursively. So now we can just cut off the 5 and we take the second half of the array. And now we take the middle and so on and so forth. So the runtime. Testing the middle building is O of 1. Sorry, it's missing there. After the test, we divide it by 2, right? So our function, our recursive function formula is T of n. We divide it by 2 every time. Each time we do O of 1 operations. So what is our final big O? Lotte? Okay, O of log n. And therefore we've solved the puddle problem. We have more problems next week. Don't worry, we have a lot more. But I just wanted to.
It's fine. Everything
Yeah.
will cover problems. It's fine. man.
Okay, yeah, you don't need any more problems in your life, is what you're saying.
Yeah.
All right, so we're done for this week.